This is a tutorial for the homework problem number 1, which is the launch vehicle transport control problem. Basically, it's an inverted pendulum on a cart model, something that we have discussed quite a lot before. So this is the cart, this is the pendulum, and we have discussed how to model this and so on. So the control is this force over here, F of t. So that's also denoted U of t in our standard control notation. And the objective is to bring this pendulum to its vertical position, so to make this angle 0. That's the objective. So if I think we denoted this by theta, right? And the objective is to stabilize the system at this vertical position. Now, in the previous homework, I asked you to linearize this dynamical system model. So we saw how this can be modeled in the form x dot equals f of x. So it's a pretty messy looking model. Okay, so here x is the position of the cart, velocity of the cart, and the theta angle and the rate theta. For this model, I asked you to come up with a transfer function which looks something like this. So I asked you to come up with the transfer function from the input u to theta, the angle, and if you did it right, you should have gotten something that looks like this: a1 s squared over s squared multiplied by s squared minus a2 squared. Okay, so you should have gotten something like this, and in fact the s squareds cancel out, so this works out to a second order system. So here all you have, the s squared on the numerator cancels out with the 1 in the denominator, and you just get a1 s squared minus a2 squared. The constants a1, a2 depend on the numerical values, and I'll leave that for you to figure out. So the objective here is to design a controller C of S, as we have seen, in the feedback form. So you have a feedback going from here to here, and we would like to design this guy C of S to satisfy the design requirements. Now I gave you multiple forms or templates for C of S. So one was the standard proportional form. So this is the simple proportional controller. So this is one, this is another template. The second template was the PD controller, KP plus KDS. So this is a proportional derivative controller. And then the third one is the PID, proportional derivative integral controller. So KP plus KDS plus KI divided by S. So that's the PID form. And you're supposed to do for this homework, you're supposed to pick one of these templates and design the KP, KD values such that the design requirements are satisfied. So here's how you should proceed. Step 1, convert the design requirements into standard form. Now, the standard second order form is something that we've seen in class, but let me just write down the step. Convert design requirements to standard form. And I'm only going to write down the standard form of the denominator of the transfer function of a second order system. That's this guy. And what I would like you to do is to take the given requirements which are in this case the settling time and the max peak overshoot. Those two things, peak overshoot, MP. I want you to take these two and find out zeta and omega n such that they would satisfy these requirements. So this is the system that you're trying to design. Step 2 is pick a control template, a template for this guy over here, and find the closed loop transfer function. So find the transfer function from this R of S to X3 of S. You know how to do this. We did this in class for a couple of times. So the trick here is to keep the parameters of your control template. So in this case, I picked a proportional control. It just has one parameter, Kp. Keep that parameter in the control or in the closed loop transfer function. Okay, so that's step number 2. So what you need to do is analytically work out what this closed loop transfer function will look like. So if you decide to go with a proportional control, this will be Kp here. If you go with a PD control, it will be Kp plus Kd times S, and so on and so forth. I gave you 3 templates before. So find the closed loop transfer function. Let's call the closed loop transfer function, I don't know, h of s. And you will find that h of s will have some numerator, which we won't worry about just yet, but it will have some denominator, which in this particular case will work out to a second order or a quadratic denominator. It'll be a quadratic denominator involving the parameters to be designed. So in this case, Kp, it will involve Kp, maybe Kd if you pick a PD control. So this is step 2, and of course step 3 is then just to pick the parameters so that they match the zeta and omega n that you picked. So that's it. That's step 3. So set the quadratic denominator of the closed loop transfer function to this standard form, except now you know numbers for zeta and omega n based on the design requirements. So that will allow you to find the parameters of your control. That will allow you to find the gains Kp, Kd, or Ki, depending on what you choose. Okay, so that's the design problem. Now, of course, you need to test your design, for which you need to do at least 2 tests. One is with the linear model itself, and the second is with the nonlinear model. So you built a nonlinear simulation of this launch vehicle transport model in the previous homework, and you're going to use that to test out the model. So let's discuss that very briefly. So there, step 4, test the controller on the linear model. Like we discussed in class, basically this is a sanity check step, right? You designed it on the linear model and you're checking it on the linear model. So all it means is that you did your calculation correct. So it does not prove that your controller is actually going to work on the real system, because the real system is nonlinear. All this test will show is that you did your linear system calculations correct. So for this, I suggest to use Simulink like we did in class. And Simulink will allow you to build a block diagram just like the one you saw in the previous 2 slides. So the transfer function a1 divided by s squared minus a2 squared. a1 and a2 are the constant that you are supposed to find out from the linearization. You did the linearization in the previous homework. Put a PID block here and set the gains of this PID block to what you found in the previous step 3. Okay, and here put an impulse. So you'd like to find out what happens to the system if it's hit by a disturbance or if it starts from a non-zero initial condition. So it starts slightly off from the vertical, for example. So to test it, just put an impulse input, and you can construct an impulse input in Simulink as a step input followed by a derivative. Okay, so there will be a delta U over delta T block in Simulink, and you'll find these under the sync. So look for sources in Simulink and look for continuous operations in Simulink, and you'll find these two blocks, put them after one another, and you get the impulse input. So the derivative of the step is an impulse. Put that as a test input, so that's your test input to see if your system works. Put a scope here, as we did in class. Put a scope here, and this scope should show you a nice plot that hopefully settles within whatever is the required settling time. Okay, so that's what you're supposed to do, and that's how you'll test your controller on the linear model. So set the right gains here, set the designed gains here. And the final test is testing with a nonlinear simulation. I mean, in the real world, the final test would be on the real system, but we don't have, unfortunately, a launch transporter at hand. So you'll test with the nonlinear simulation that you built. The only trick here is to set the correct input. So here in this step, you will put the initial conditions given, right? Use the given initial conditions to test. Given initial conditions, and the feedback control input now takes the form, it's the PD form, and the only trick here is to write the correct PD form in the time domain. So I've shown you as Kp plus Kd times S, and all you have to do now is in the simulation make sure you have U of t equals Kp multiplied by theta reference minus the actual theta. Okay, and I'll talk to you about what theta reference is. It's just 0, but this is the most generic form, plus Kd multiplied by theta dot reference minus theta dot. Okay, so both of these are 0. So all you have is Kp multiplied by negative theta and Kd multiplied by negative theta. Desired minus actual. So this is just equal to Kp theta minus Kd theta dot. Now both of these are your state variables, right? So this is x3 and x4. So what you really have is U of t is equal to minus Kp x3 minus Kd x4. So that's your, I put the minus sign outside, so this will become a plus. So that's your control, and that's all you need to do. So with the nonlinear simulation, you need to check whether this control system designed with the linear form, right? So you designed it for a simpler model. That's why we need to do this check, and this is not just a sanity check, this is actually a fundamental check. We don't know if the control we designed is actually going to work on the nonlinear model, so that's what you need to identify. If it doesn't work, or maybe it works kind of, but it doesn't give you the performance, your job is to then tweak these gains, Kp and Kd, such that you get slightly better results. So that's it. That's the first homework, and in fact the second problem is identical. You just have a different system to work with, but the idea is exactly the same. So you can follow these exact same steps for the first two problems and finish them fairly easily.